Welcome back to linear algebra. Last time we talked about subspaces. Today we're going to talk about the null space. So the null space of an m by n matrix A is the set of all solutions to ax equals 0. But more precisely, it's the set of all x such that x is in Rn and ax is equal to 0. So for instance, if we have 0 in Rm, we have this set of solutions in Rn such that they all map to 0. So these are x's that map to 0. So this little area here is going to be our null space. So here's an example question when talking about null spaces, a nice computation question. So is this vector u, 5, negative 3, 2, in the null space of A, where A is equal to this matrix? So how do we check this out? Well, the null space is the set of vectors such that AU is equal to 0. So we just have to check that AU is equal to 0. So let's take our matrix A, which is 5, 21, 19, 13, 23, 2, 8, 14, 1. And we'll multiply this by 5, negative 3, 2. So if we do our AX equals B multiplication, this is going to be 5 times the first column, so this will be 25. 13 times 5 is 65. 5 times 8 is 40. Then we're going to add negative 3 of the second column, so this will be negative 63, negative 69, and negative 42. And then we'll add 2 times the third column. This will be 38, 4, and 2. And our result is 25 plus 38 is 63, minus 63 is 0. 65 plus 4 is 69, minus 69 is 0. 40 plus 2 minus 42 is 0. Therefore, we have the 0 vector. So, because A times U produces the 0 vector, then U is going to be in the null space of A. So we're good. Okay. So if A is m by n, then the null space of A is a subspace of Rn. So we want to prove this. So of course we're talking about spaces, and you think, hold on, if we're calling it a null space, it's probably going to be a subspace. So you would be right there. But we need to prove this. So how do we prove this? Well, first we have to check if 0 is in null A. So we're saying null A is a subspace, so we have to show that 0 is in null A. So how do we do this? Well, remember, null space, I'll write out this definition again on the side. So null A is the set of all x such that x is in Rn and Ax is equal to 0. Okay, so what this means, if 0 is in null A, this means that A times the 0 vector has to equal 0, or the 0 vector. And of course we know this is true. So anything times the 0 vector, you're going to get the 0 vector back, assuming it can multiply nicely. Okay, number 2, we need to show that if U and V are in null A, then we get U plus V in null A. Okay, so we need to pick our U's and V's. So we're not going to pick anything specific. We're just going to say, okay, so suppose that AU is equal to 0 and AV is equal to 0. So if these two equal 0, then we know that U and V are going to be in null A. So we need to show that U plus V is in null A. So what does this mean? This means that A times the vectors U plus V has to be equal to the 0 vector. Well, we know from our matrix vector laws that A times the vector U plus V is the same thing as A times the vector U plus A times the vector B, which is just equal to the 0 vector plus the 0 vector, which is equal to the 0 vector. Therefore, A times U plus V is equal to 0, so this is in the null space of A. Okay, third one. We need to show that C times U is a null A for any c in the reals. Okay, so again, we're just going to suppose that a times u is equal to the 0 vector, and then of course if we have a times c times u, then with our matrix vector laws we can just take out the c. So this is going to be the same thing as c times au, and we know this is just equal to c times the 0 vector, which is equal to the 0 vector. Therefore a times cu produces the 0 vector, so cu is in the null space of A for any c. So we've proven here that the null space of A is a subspace of Rn. Okay, so what if we're asked to find explicit solutions to null A? So for instance, I want to find the spanning set of AX is equal to 0. So this is another way of saying I want to find the solutions to null A. So we have a matrix A here. What we need to do is we need to reduce it to echelon form. So reduced echelon form. So let's do that. The first column is set up nicely. I wonder why that is. And the second column is a 3 in the first row, 1 in the second row. We need to get rid of that 3. So we're going to subtract 3 of the second row from the first. So 1 times 0, or 1 minus 0 is 1. 3 minus 3 is 0. 5 minus 12 is negative 7. 0 minus negative 6 is 6. And the second row is okay. So now we can rewrite this solution. We can say that x1 is equal to 7x3 minus 6x4, and x2 is equal to negative 4x3 plus 2x4. So what I did here, of course we know this is x1, x2, x3, x4. I set the row equal to 0, and I flipped it to the other side, so we're isolating x1 and x2. So this is, the first row is like saying x1 minus 7x3 plus 6x4 is equal to 0. I just moved the x3 and x4 to the other side. Okay, so what does our solution look like? Well, our vector x, I should just write this like this, vector x is going to be x1, x2, x3, and x4. So we can rewrite this as 7x3 minus 6x4. x2 is going to be negative 4x3 plus 2x4. x3 is equal to x3, and x4 is equal to x4. Okay, let's do some factoring. So we have x3 times, it's going to be 7, negative 4, 1, and 0. If we factor x3's out, then we're going to add x4. And if we factor x4's out, we're going to get negative 6, 2, 0, and 1. Okay, so that is incredibly messy. Okay, there we go. So here is our spanning set. So we have this constant times our vector and another constant times a vector. So we can be more specific here. And we can say that the spanning set is going to consist of these two vectors. So 7, negative 4, 1, 0, and negative 6, 2, 0, 1. And of course we can say this is the span. So this is the explicit solutions to the null space. So if we want to find any vector u such that au is equal to 0, then we can just pick any linear combination of these two vectors and we'll produce the 0 vector. So that was the null space. Next time we'll talk about the column space. So if you have any questions, please leave them in the comments below and I'll answer them the best that I can.